All right. Okay, so all right. Okay, so I presume some of you must be surprised, like why am I taking this lecture? Well, I couldn't complete what I wanted to cover before the midterm, so I thought I'll take one more lecture. So Professor Vijay Natarajan, okay, will be teaching from the next class. Okay, Natarajan. Okay, so Professor Vijay Natarajan would be teaching from the next class. That is, if I'm not wrong, that would be on 1st of March. Okay. Uh, okay, so I wanted to, maybe cover one class on this topic called as random topology. Um, so let's try to discuss that. Okay. So random topology basically concerns topology of random spaces, right? Like for example, we could look at topology of manifolds and things like that, where these spaces are, constructed using some random process and so on and so forth, right? However, since my part of the course focused on simplicial complexes, we will focus on topology of random simplicial complexes. Is that okay? So I mean, it is sort of not difficult to see that this topic lies at the intersection of several areas. Okay, the main ones amongst these are combinatorics. So, I mean, in the examples that we will see today, you will notice that we do a lot of counting, right? And since there is some randomness involved here, of course, the topic of probability comes in. So there is, we are interested in studying topology. So the area of algebraic topology comes in, and this area, okay, the study of random topology of random simplicial complexes has now started finding several applications in statistics and data analysis. In fact, there is a new area by the name topological data analysis that is gaining attention across the world. Okay, so topological data analysis. All right. Okay. So, but nevertheless, in today's class, we will just give a very brief overview. Okay, and if you are interested, you can talk to me after the class, or maybe whenever you are interested. Okay, so and today's discussion will mainly focus on these three topics, that is combinatorics, probability, and topology. Right. So whenever we study a new topic, at least I often ask a question like, why should we study this topic? Right. So before we try to answer this question, okay, we will try and answer this question in a simpler context, that is of random graphs, right? So I'm sure all of you here are aware that simplicial complexes are an extensions of graphs, right? Are extensions of graphs. So in that spirit, random simplicial complexes are extensions of random graphs, right? So each random graph can also be thought of as a random simplicial complex. So one can first try and answer this question, why study random graphs? Okay, so this answer, okay, was given by this Swedish mathematician by the name Svante Jansson. Okay, so there is a J, but I don't know why, but they pronounce it as a Y. Okay, so if I'm not wrong, this rule comes from the Russian language. So anyways, uh, so this name is to be pronounced as Swan Janssen. I don't know how to pronounce the first name, but the last name is Janssen. Right. So this answer, so he is a very popular mathematician. In particular, he has made significant contributions in the study of random graphs. Okay, so he sort of tried answering this question: why should we study random graphs? Right. So he sort of approached this question from two perspectives. The first one was from the viewpoint of a theoretician or a mathematician. Okay, and he said that, well, random graphs are interesting because they provide really interesting problems, and hopefully we will see an example of one such problem later on, right? And this problem is interesting, from the perspective of probability and combinatorics. And often these questions, you will see that they are very easy to state, right? So this is unlike other branches, like let's say mathematical finance, or other topics where the questions themselves are quite technical, right? So in order to understand the question itself, you need to understand a lot of technical jargon and so on and so forth. But that's not the case in this topic of random graphs. You can in fact pose this question even to high school children, or maybe some of the brighter ones, in the brighter ones among the younger students as well, right? So one can actually pose these questions, and often they are easy to pose. However, what one has realized is that while the questions may be very, very easy to pose, answering them often turns out to be quite difficult. In fact, answering them often, requires developing completely new theory, okay, and so on and so forth, right? So this is from the perspective of a theoretician or a mathematician, why he should look at this topic of random graphs. The answer is that, there are several interesting problems over there which are easy to pose, but often quite hard to answer. Okay, and then one can ask, okay, this is from the theoretician's side. What about from an applied mathematician side, or let's say from a computer scientist side, right? So here are a bunch of situations where random graphs may be of use, right? Like for example, if you are interested in studying how diseases spread, right? So in this case, you may model, your different individuals as vertices in a graph, and whenever two vertices meet, let's say I put an edge, and if one of these persons is infected, and if these two persons meet, then if one is infected, we will sort of assume that the disease will spread to this person as well, right? And you can see that one can sort of model or use a graph to model the interaction between different individuals, and in that sense you can use a graph to study the spread of diseases, right? However, this graph, okay, is often unknown, right? Like, who, let's say I give you the citizens of a particular city, right? Then it is very difficult to figure out who is going to meet who and at what time, and so on and so forth, right? And in that sense, this graph is unknown, and it keeps changing, right? So it keeps changing because maybe this person meets this person at this point, right? But later on, maybe they sort of move away, and maybe this person meets this person, and so on. So you can see that while on the one hand this graph is unknown, and on the other hand this graph keeps evolving, right? So in this situation, since the evolution of this graph, how it evolves and so on and so forth, is very difficult, and there is a lot of uncertainties involved, it makes a lot of sense to model this entire evolution by using a suitable stochastic process. Okay, so we can sort of use a stochastic process or a random process, right? A random time involving process to model such an evolving graph, right? So you can see that here again some randomness may be useful in the graphs to model this evolution, right? And the other popular setting where random graphs could be of use is to describe the structure of the internet, right? So you can imagine that this internet is very, very complicated, right? So if one wants to model all the connections in the internet, okay, so like for example, the nodes will be the different entities that are involved, maybe your computers, maybe the different routers that are present, maybe the different servers that are present, and so on, right? And edges could be if these two nodes communicate, and so on and so forth. So if you try to build the picture of the internet, I'm sure it is going to be very, very hard for you, right? However, what you can do is maybe you can take a snapshot of the internet, right? Like maybe that is one that is there in your neighborhood, okay, use that and make some guesses about how the whole internet may look like, right? So you can again see that this question can be viewed from the perspective of statistics, that you are looking at a sample and using that to say something about the whole population, right? So you can see that here again the study of random graphs and understanding its behavior will help you in this endeavor, right? So so these are some typical use cases of random graphs, both from a theoretician's perspective and from an applied mathematician's perspective, right? So one can in particular ask, okay, let's say random graphs are useful, but how would studies on random graphs actually help, right? So the studies on random graphs could help us in the following way, right? So the first thing is, let's say you have a graph from a real data, right? So let's say you create a graph, let's say about researchers at IISc, right? So let's say this is researcher 1, this is researcher 2, this is researcher 3, and so on, right? And let's say you put a edge between two researchers if they have collaborated on a paper, right? So they have collaborated on a paper, right? So in this way, I hope you agree that you will end up with some graph, right? And you see something that is interesting about this graph. Let's say you find that this graph is connected, right? So you find some pattern in this graph and you would like to ask whether this pattern that you have identified, okay, like let's say the graph is connected, or maybe there are, several cycles in the graph, right? So you observe some patterns. So the first thing you would like to ask is the pattern that you have seen in this actual graph, right? So this is an actual graph, right? And or by actual graph I mean a graph that concerns some real data, right? So you observe some pattern and you would like to ask whether this pattern that you have observed, whether it is significant or not, right? So if you are a student of statistics, I hope you would agree that this is one of the fundamental questions, that whenever you observe some pattern, okay, in any data, the first thing you have to ask is whether it is significant or not, right? So how does one answer this question whether this observed pattern is significant or not? Well, the loose idea is the following, right? You sort of ask, let's say I create a simple random graph, right? So on the one hand you have the graph from the actual data, on the other hand you have a simple random graph, and you can ask whether a simple random graph can reproduce the interesting features of the kind that you observed in the real data, right? Like for example, let's say your graph that you observed was connected, right? And let's say the simple random graph that you saw, you can somehow or you are that is of interest to you, okay, you saw that this simple random graph also has a similar feature, that is, let's say it's also connected, right? So in that situation, okay, this observation that the random graph model also gives you these interesting features, then that may be a strong indication as to not give too much importance to these features and waste time inventing complicated explanations, right? So let me try and repeat this. So you look at the graph from the actual data, you find an interesting feature, right? And you wonder whether this is this feature is indeed interesting or not. The thumb rule is that if the same feature can be easily reproducible in a random graph, right, then one would say that, look, a random graph itself can generate it, then observing this feature in this actual data may really not be interesting, right? So we shouldn't waste time to invent complicated explanations. However, if on the other hand this random graph fails to reproduce some of the properties that you have observed, right? So like let's say you observe too many cycles in this graph, right? And let's say in this random graph you see that, look, having too many cycles is not possible, then that automatically implies that there is something interesting that is happening in this in this actual graph, and that is something that we should spend time investigating, and it is meaningful then to spend time studying it, right? So I hope I have managed to give you a loose idea of why studying random graphs and how these studies could be of use, right? So one can now ask, okay, random graphs are useful in this sense, why to study random simplicial complexes? Well, the answer is that, okay, random graphs are useful only to model binary relations, right? Like in this example that we saw, right here we said, we will put an edge between two researchers if they collaborate on a paper. But I'm sure you all know that in one particular paper, more than two authors can collaborate, right? You could have three authors, you could have four authors. In fact, some of these physics papers, related to nuclear energy or blah blah blah, you will see that there will be thousands of authors on those papers, right? So in that situation, clearly this graph is not capturing all the information that is available. So in such situations, these random simplicial complexes will definitely be of help, right? So I hope this is clear. So I will pause over here for a second or two. If you have any questions with regards to what I said, this may be a good time to ask. Please let me know. Do you have any questions? All right. Okay. So I don't see any raised hand. So maybe we advance and look at some specific questions. Okay. So our question, so our goal right now is to, study some of the questions related to topology of random simplicial complexes. Okay. So since this is the first class on random simplicial complexes, I don't want to do anything complicated, but rather focus on some simple questions and, allow you to sort of imagine what would be the complicated versions of these questions, right? So instead of directly beginning with random simplicial complex, let us begin with an example of a random graph model and try to ask some very, very simple question in this, right? So the simplest random graph that one can think of is what is called as the Edosh-Renyi model, right? So Paul Edosh and Alfred Renyi, these are some of the two of the most what should I say popular or famous probabilists. In fact, Paul Edosh is a really, really famous guy. In fact, some of you may have also heard about something called as this Edosh number, right? So if you don't know, maybe you can read a bit about this Edosh number. Okay. Anyways, okay. So uh, so these are the two guys, on which this model is actually named. Okay, so in this random graph model, the notation that we use for this random graph model is Gn comma P. Okay, so G here is the graph. N here denotes the number of vertices. So let's say we label the vertices as 1 to n, and the P here denotes the edge probability. So what do I mean by that? Each edge is present in this graph with probability P independently. Okay, so let me elaborate this a bit more. So let's say you have n vertices, right? So let's say you have n vertices, right? And now I hope you agree that in all there are n choose 2 possible vertices, right? So you can have 1 2 1 3 1 4 so on up to 1 n, then you have 2 3 2 4 and so on, then you have 3 4 3 5 all the way up till 3n. So in all you will see that there are n choose 2 possibilities. So what we do is we sort of go to each pair, okay, and we ask when would there be an edge between these two vertices. Well, what we do is we sort of, let's say you have a coin, and let's say the probability of head in this coin is P, right? So let's say you have a biased coin and the probability of head appearing on this coin is P. So the way you will put edges in this graph is that you will go to each pair, you will toss this coin. If there is a head, you put an edge between these two vertices. If there is a tail, you don't put an edge, right? So in this way, I hope you agree that you will end up with some graph like this, right? So let's say this is vertex 5 maybe. So you have an edge between 5 and n. Maybe you have a edge between 3 and maybe 7 and so on, right? So I hope you agree that in this sense, you will get a random graph, and each time you sample this random graph, I hope you agree that you'll end up with a different graph, right? So let me pause here for a second or two. If you have any questions with regards to understanding this Edosh-Renyi graph model, please let me know. I'd be happy to explain. Please let me know if you have any questions. All right, so I don't see any raised hand, so maybe we can continue, and I'll presume that each one of you has understood what this simple Edosh-Renyi model is, right? So we have this Edosh-Renyi model, right? And one can ask this question, right? So how many components are there in this graph? Do you agree? So how many components are there in this graph? So I hope you agree that, in terms of these Betti numbers, the zeroth Betti number concerns the number of components in GNP. So what we are really interested in is we sort of have this random graph, right? So random graph, by that I mean each time you sample this graph, you could possibly obtain a different graph. So what we are interested in knowing is what is the zeroth Betti number of this graph, which is equivalent to asking how many components are there in GNP, right? So, I hope the first thing you will agree is that this beta 0 NP, right? So this is the notation that we will use. So beta 0 NP is basically the number of components in this GNP graph, right? So I hope all of you agree that this is a random variable, right? So this is a random variable, and we are interested in knowing some properties about this random variable. Okay, so that's the question. This is the simplest question that one can pose, right? So I hope you agree that posing this question is very, very easy, right? So even if someone didn't understand really what these Betty numbers are and so on and so forth, nevertheless, I can explain to him what a component means. I can explain to him what this random graph is, and I can ask him how many components are there in this graph, right? So I hope you agree that explaining this question is not really that hard. However, you will soon see that even though this question is so easy to pose, right, answering it actually required several papers. Okay, and some of these papers have been published in some of the top journals related to probability, right? So and I will only be able to give a glimpse of some of these results. If you are interested, you can sort of look it up on your own. All right. Okay, so let's before we try and answer this question, let's try to ask why would one think this question is interesting, right? So of course, from a theoretician's perspective, this is easy to describe why it is interesting, right? Because this is a simple graph, and this question itself is quite interesting, and maybe one as a theoretician, one can ask if the answering this question is easy or not, and so on and so forth, right? So however, when I pose this question, I'm more interested in knowing how could this be of use to a practitioner, right, to an applied person, right? So let me try and cook up an example where such a question could be of use, right? So the question is the following: you have this Edor-Shreni graph, and we are interested in knowing the number of components in this Edor-Shreni graph, right? So this is a cooked up example. Okay, so you don't have to read too much into it, but nevertheless, while this example may be cooked up, you will soon see that one can sort of extend this and come up with a problem that is of use in real life. All right, so here is the cooked up example. Let's say I pick n students at random from IISc, right? So I sort of pick n students at random from IISc, right? And let's say I use n vertices to denote them, uh, n vertices to denote each of these students, right? So 1 over here denotes the first student, 2 over here denotes the second student, and so on, right? And I will put an edge between any two of these students if they meet at least once. Okay, we put an edge between a pair of students if they meet at least once every r days, right? So r is some parameter at this point. So like for example, you could choose r to be 2, or maybe r to be 0.5, and so on and so forth, right? So you can take r to be some parameter. So at this point, I'm leaving it as a parameter. So I'll put an edge between any two students if they meet at least once every r days, right? And if they don't meet at least once every r days, then I will not put an edge. So I hope you agree that I may end up with some graph like this and so on and so forth, right? So let's say I am a person who is selling a product, right? And I have some limited budget, so I cannot advertise this product to all the n students. But what I do is, maybe I pick the first student from amongst these n students, and I advertise my product to the first student. Then I can ask, will the other n minus 1 students become aware of my product or not, right? So I hope you agree that these are the n different students that I have. So what I have done is, I have gone and shown or advertised my product to the first student, and then I would like to ask, will this person interact in some sense with the other n minus 1 students, and will the other n minus 1 students become aware of my product, right? So to answer such a question, I hope you agree that if this graph was connected, right? If this graph was connected, right? So maybe the connections could be this way, that okay, so let's say I'll come up with So let's say n is 10, right? And n is 10, and let's say we have a graph like this, right? So which means that 1 and 2 meet frequently, right? Which means that they meet at least once in R days. That's why I have an edge between them. 2 and 3 similarly meet once every R days. That's why there is an edge. And let's say 3 is a popular person, and because of that he meets 2, 4, 5 often. That's why there is an edge between 3 and 4, 3 and 5, right? And 8 is maybe an even more popular person, so he meets all these students, right? And so on and so forth, right? So if I advertise to the first student, right, we will presume that whenever 1 meets 2, maybe he mentions about my product to 2, and whenever 2 meets 3, 2 mentions about my product to 3, and 3 similarly mentions about my product to 4 and 5, and 5 maybe informs to others, and so on and so forth. So it is easy to see that if the graph is connected, then there is a high chance that everyone will become aware of my product, right? So even though I have only advertised or given a demonstration to student 1, everyone over here will become aware of my product, right? So if I have limited budget, I don't have to advertise to all the students. It suffices for me to just advertise to one student, and I will hope that whenever they meet, they will talk about my product, and in turn everyone becomes aware, right? On the other hand, right, if let's say in this situation, the graph had the following form, right? Let's say 1 2 1 meets 2 and 2 meets 3. However, 3, maybe he meets 2, but maybe he doesn't meet anyone else, right? On the other hand, let's say you had 4 meeting 5, 5 meeting 6, and maybe so on and so forth, right? So what I'm trying to say is, let's say you had some sort of situation where you had more components than one, right? So in this situation, clearly, okay, giving a demonstration to just student 1 doesn't suffice, right? We would want to maybe advertise to one student over here, one student over here in this group, and maybe one student to over in this group, right? So you can clearly see that how many times should I advertise will depend on the number of components that are present over here, right? And since these n students were chosen randomly from this the whole set of students at IISc, right, the connections that I will end up with, okay, I hope you agree that the Edosh-Shreni model would be a decent model to model this scenario that we have. Is this okay? So you can see that even answering this cooked up question, whether I have to advertise to just one student or maybe more than one student, okay, even to answer such a question, I hope you agree that knowing the number of components in this graph, okay, indeed makes a lot of sense, right? So let me stop over here for a second or two. If you have any questions, please let me know. Otherwise, we can go ahead. Yes, Ichit, please go ahead.
I want to ask whether this DOS training model is just defined for the undirected graph, or is it defined for directed?
So Edosh-Shreni by itself is an undirected graph. If that is your question, yes.
Okay, so similar model is defined for directed as well.
So one can cook up. See, these models are not something that come from God or something. These are models that we construct on our own, right? So if you think that a directed graph model is going to be useful to model the scenario that interests you, you can go ahead and cook up your own directed graph model. Is this okay? So if your question is, are there models similar to the Edosh-Shreni graph? I mean, of course, there are plenty of models where you can put edges, directed edges as well, right? But the Edosh-Shreni model is the one that has been extensively studied. That's why there is like a it is named after these famous probabilists. I hope that answers your question. Is that fine?
Yes, sir. Thank you.
Okay. Okay. Durjati, please go ahead.
Sir, you have told that a simple random graph would generate a complex random graph. What means how it will generate? I didn't understand.
Did I say that a simple random graph will generate a complex random graph? Is that
No,
the
no, no. You haven't said that. I mean, it will generate all possible graphs, and if the complex form falls under that graph, then
So what I
means
mean is, let's say, I mean, my point was, see, I hope you agree that this Edo-Shreni model is a very simple model. Do you agree? Right?
yes, yes.
Now, what I'm saying is that, let's say you have an actual graph meaning, let's say you had some data, which can be viewed as a graph, and you observed some feature in that graph, like let's say it is connected. Do you agree? Right? Now
Yes,
you can ask, so this is a feature that you observe. So before you go ahead and do something about this feature, you have to ask whether this feature is significant or not. Do you agree? Right? And one way to answer whether an observed feature is significant or not is to check if the same feature can be easily reproduced in a random graph model. Is that okay? That's what I said.
okay, okay.
Is this okay? Now, that's the kind of question that we are asking over here, right? Like here is a scenario that you could observe, right? And we are interested in knowing what could be the features of such a graph, right? So what we are trying to say is, okay, this scenario can be modeled like a Edo-Shreni graph, and we can sort of study the features of the Edo-Shreni graph and sort of make predictions about what the different features of this graph would be. In particular, at this point, we are interested in knowing how many components would be there in this graph. Is this okay? That's the question
Yes,
that we are interested. But of course, we can ask several questions. But at this point, we are only focusing on the the number of components in this graph. Does that help?
yes, sir.
All right. Okay. So, let's make some trivial observations. So I hope the question is clear to everyone. We have the Edo-Shreni graph and we are interested in knowing the zeroth Betti number of this graph, which is equivalent to knowing how many components will be there in this graph. Okay. So I hope you all agree that this is a question which is very, very easy to state. Nevertheless, as you will soon see, answering this question is really, really hard. And, there have been several papers that have been written over several decades, okay, in order to answer this question. All right. Okay, so let's make some trivial observations. The first is that the zeroth Betti number is a random variable, right? So I hope you all agree. By a random variable, I mean that each time you sample this random graph, this beta 0 may take a different value, right? Nevertheless, I hope you all agree that when P is 0, so P, recall, is the edge connection probability. So if P is 0, then beta 0 of NP would be N, right? Because if P is 0, there will be no edge, right? And basically all your vertices will be isolated, right? So on, and let's say this is n minus 1 to n. So since there are no edges between any of the vertices, you will have these isolated vertices, and consequently one can conclude that the zeroth Betti number in this situation would be n, right? So now let's look at the other scenario when P is 1. So what does P equals 1 mean? P equals 1 means that all the edges are present, right? So all the edges are present, meaning you will have a scenario something like this, right? And so on, right? So I hope you agree that you will end up with a complete graph, and because it's a complete graph, right, the whole graph is connected, and consequently we will end up with a scenario where the number of components is 1, right? So I hope you all agree that when P is 0, the number of components is n, whereas when P is 1, the number of components is 1, right? So these answers do not depend on the value of n. Whatever be n, this will be the answer, right? So of course these are non-interesting cases, because answering this question is very easy here. So the interesting case is when P is a number which is strictly between 0 and 1. Okay, so that is the case that is interesting to us, right? So the question that we wanted to ask was can we say something about beta 0 of this graph, that is the number of components in this Edo-Shreni graph, right? So answering this question, as you will soon see, is quite hard. So what we will do is, instead of trying to answer this question in full generality, we will at least, for the time being, we will focus on trying to figure out what is the expected number of this random variable, right? So the question that we are interested in knowing is, let's say GNP is this Edo-Shreni graph. What is the expected number of components that I will see in this graph? Okay, so that is the question that we will focus on. Okay, so I hope you agree here at a level of intuition that as we add more edges, right, the number of components will only decrease, right? Let me repeat, as we add more edges, the number of components is only going to decrease. Hence one would expect that if P is less than P prime, right? So P and P prime are two parameter choices for this edge connection probability. So if P is less than P prime, then the expected number of components with P as a parameter, this will be more than the expected number of components with P prime as the parameter, right? So because when we have P prime bigger than P, this would imply that on an average there will be more edges in Gn prime, GNP prime, right? So there will be more edges here as compared to the number of edges in GNP, right? So on an average you would have more. So one would intuitively expect that this relationship holds. Nevertheless, okay, you can try it on your own, but you will soon see that getting the exact values, like what is this expected value for this choice of P and all, okay, so that turns out to be quite hard in general, right? So so then we have to ask, okay, so answering this question is not that easy. So can we do something that is that helps us answer this question, right? So here is an interesting observation in that direction, right? So an interesting observation is that every isolated vertex contributes a component, right? So in that spirit, the number of isolated vertices, right? So sorry, I think I made a mistake in that statement. Every isolated vertex contributes a component. That's why the number of isolated vertices is a lower bound on the Betti number, right? On the zeroth Betti number. I think I should stress that. So this should be the zeroth Betti number, right? So every isolated vertex contributes a component. Hence, the number of isolated vertices is a lower bound on the zeroth Betti number, right? So more formally, right, if INP denotes the number of isolated vertices in GNP, I hope you agree that beta 0 of NP is lower bounded by INP, right? So what is very, very interesting about this relation is the following. What is interesting is that here is Betti 0, right? And what we have done is we have approximated this by something that is easy to count, right? So one can ask, okay, what is so hard about this beta 0 of NP? Well, the hard thing about beta 0 of NP is that in general, any beta k, if you recall, this is defined to be the dimension of some vector space, right? So beta k is the dimension of the kth homology space. So in that sense, it's a dimension of some vector space. So because of that reason, okay, since it's a dimension of a vector space, identifying how many basis elements are there and so on and so forth, okay, that in general is quite hard, right? Like in general, if I give you a matrix and I ask you what's the rank of this matrix, that itself, I hope you agree, is a quite a hard question to answer. So this dimension of HK is in that spirit, that we are sort of interested in knowing the rank of some matrix or something like that. So because of this reason, knowing beta k or trying to estimate beta k directly is hard. However, what this relation tells us is that while this the quantity on the left hand side may be hard to work with, the quantity on the right is easy to work with, right? As we will soon see that the quantity on the right is actually easy to work with, and you can see that whatever I can say about this, that will tell me a lower bound on beta 0 of NP. Okay, so while this may be a very, very simple relation, however, this sort of philosophy dictates the whole of study of random simplicial complexes. So the idea is that while Betti numbers or topological terms themselves may be very hard to study, what you do is you come up with an approximation to these quantities, and these approximations should be of the nature that they themselves are easy to study, and they provide some information about these Betti numbers and these topological quantities that are of interest to us. Okay, so let me pause here for a couple of seconds. If you have any question with regards to what I said, please ask. Yes, Pankaj, go ahead.
Yeah, I did not understand actually why the Betti 0 is tough and counting isolated vertices is easy, because Betti 0 itself is counting the number of components, right?
So let me just understand your question. Your question is, you are not clear why this lower bound holds. Is that correct?
No, I understand that lower bound holds, but I did not understand why calculating Betti's 0 is tough, but counting isolated vertices is easy. That's what I did not understand.
What is not clear to is why counting Betti zero is equivalent to counting isolated vertices. Is that your question?
I mean, I'm saying why one is easier and why one is tough.
Oh, why one is easier and why one is hard, right? So,
yes.
So okay, so that question I can answer. So I will see. I haven't told you why counting these isolated vertices is easy. I will show you on the next page why it is easy, right? But see, this Betti zero is hard because of the reasons that I mentioned. Beta zero is the dimension of a vector space, right? So computing the dimensions of matrices or rank of matrices in general is very hard, right? So estimating the properties of what the rank would be and so on and so forth, right? So that in general is hard. Okay, why it is hard and so on and so forth. I mean, you can try doing it on your own and you will see that you are not able to figure it out, right? However, I'll teach you how to do this and you will soon see that this is actually something that you yourself can do. Okay, so that is like maybe a naive answer, but you can read up on literature and see that computing the rank of these random matrices and so on and so forth, okay, that is in general quite hard. Okay, so now maybe I'll try and explain why computing this INP is actually easy. Okay, so let me sort of explain that, and you will be able to maybe appreciate why this part is easy and why this part is relatively hard, right? So what I'll do is I'll define this indicator variable, right? So what is this indicator variable saying? So first of all, say that this indicator variable is indexed by I. So this variable is 1 if vertex I is isolated in GNP. Is this okay? This variable is 1 if vertex I is isolated in GNP and 0 otherwise, right? So now I hope you agree that INP equals sum of indicator I, where I goes from 1 to n. So basically I'm checking if vertex I is isolated. So I'm basically checking if vertex 1 is isolated, vertex 2 is isolated, and so on, all the way up till vertex n. So I hope you agree that if I check for all the vertices whether they are isolated or not, this sum will equal INP. So let me pause over here. If you have any questions on what we have discussed so far, please let me know. This relation, if you understand, you will immediately be able to figure out why computing statistics about INP is quite easy. Okay. Do you have any questions? Please let me know. Yes, Jacob, please go ahead.
1i is a random variable, right?
1i is a random variable, but this random variable says something about vertex I. Okay.
Okay.
Is this okay? Right? It's indeed a random variable because each time you generate a sample of a graph, right? It is possible that in one sample vertex I is connected to some other vertex, whereas in some other sample vertex I is not connected to any other vertex. So in that sense, it's a random variable. Is this okay? Any other question?
Yes.
All right. Okay, so the important thing over here is that INP can be expressed as a sum of random variables, right? So whenever I say it's a sum of random variables, I hope automatically these law of large numbers, central limit theorems, and so on and so forth, they sort of kick in, right? So in that sense, okay, such quantities have been very well studied in probability. So whenever INP can, because INP can be expressed as a sum of random variables, right? One can say a lot about INP as compared to beta 0 NP. So Pankaj, does that answer your question somewhat?
Yeah.
Right. So this is the reason that you can express this as a sum of random variables, right? Okay. So now what I will do is, we can say much more about INP, but our focus will be on expected value of INP because, as I said before, our interest was on focusing on this expected value of beta 0 of NP, right? So this was our focus. Hence, we will restrict ourselves to looking at expected value of INP. So my first claim is that expected value of INP is sum of expected value of 1i. So can one of you tell me why is this relationship true? Yes,
Linearity of expectation.
please raise your hand. I cannot see who is talking. Please raise your hand. Yes, Pankaj, go ahead.
linearity of expectation.
So just a quick question to you. Does linearity of expectation require that these random variables that are there inside this summation be independent?
No.
No, very good. So that is very, very important. So even though I haven't checked whether these random variables one, so I hope you agree that there are n random variables over here, 1, 1, 1, 2, blah, 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 1, n, right? So I haven't checked whether these random variables are independent or not, right? So even though I haven't checked them, I'm saying that this relationship holds because linearity of expectation, this property doesn't require these random variables to be independent, right? So now I'm saying that this equals this. So can one of you please volunteer and tell me why this relationship is true? Why is this relationship true? Yes, Jacob, please go ahead.
Each vertex is considered independently, and the same probability
Independent is not the right word. So each vertex over here is identical to any other vertex.
Yes, okay.
Is that okay? So if you sort of look at this Adorst-Reni graph, no vertex is more special than any other vertex. Do you agree? Right? So
Yes.
all the vertices over here are of a similar nature. So which means that all these expectations, in particular, the expectation for each I would be the same. Hence, one can write this as n times expected value of 1, 1. Okay, and why have I chosen it as 1, 1? Well, I could have equivalently written this as n times expected value of 1, 2, but I can write it in any way. So I chose this just for convenience. So let me pause here for a second or two. Please let me know if you understood how I derived this expression. Okay, so I don't see any raised hand, so maybe we can advance. So now I'm claiming that this quantity is 1 minus p raised to n minus 1. So can one of you please justify why is this true? Why is this true? Yes, Agnit, please go ahead.
So there are n vertices total. So the first vertex can have at most n minus 1 neighbors, and each of these does not occur. So that comes with probability 1 minus p, and each edge is independent. So the probabilities are multiplied.
Precisely. Okay, so very good explanation. So observe that there are n minus 1 edges here. So we require that this vertex be isolated. So which means that none of these edges should be present. So none of these should be present, and all these, this edge being present or not is independent of whether this edge is present or not, and so on. So this edge being present or not, or this edge being absent, has probability 1 minus p, and there are n minus 1 edges, and consequently this probability will be 1 minus p raised to n minus 1. Okay, so if you have any questions, please ask. Otherwise, I hope all of us agree that the expected value of the number of isolated vertices is n times 1 minus p raised to n minus 1, right? So you can see that even though we don't know expected value of Betti 0, by knowing the expected value of the number of isolated vertices, we now have a lower bound, right, on expected value of Betti 0 of np, right? So this is greater than n times 1 minus p raised to n minus 1. Is this okay, right? Okay, so whenever we come up with some expressions, it's always encouraged to do a sanity check. So we have this expression. So let's see what happens when p is 0. So when p is 0, this entire expression will be 1. 1 raised to anything is 1, and consequently this expected value will turn out to be n, right? So this actually makes sense because when p is 0, none of the edges are present, which means that you will have n vertices and n isolated vertices, and consequently expected value this must be n. On the other hand, when p is 1, right, this quantity over here will be 0, right, and hence this product will be 0, which makes sense because when p is 1, you have a complete graph and the number of isolated vertices will be 0, right? So this sort of makes sense. All right, so now let's look at the case where p is some constant between 0 and 1, right? So p is some constant, like for example, let's say you choose p to be, let's say 3 over 4, or maybe p to be 1 over 4, or maybe p to be 0.1. Whatever you choose and you fix it. and this will be constant with respect to n, where n here is the number of vertices, right? So this will be a constant with respect to n. Now, can one of you tell me why does this relationship hold then? So I'm claiming that when p is a constant between 0 and 1, this expected value decays to 0 as n tends to infinity. Can one of you tell me why? Why is this relationship true? Please raise your hand. I cannot see. Yes, Pankaj, go ahead.
Because 1 minus p will be a number between 0 and 1.
Very good.
When n is going to infinity, that will keep on reducing.
Okay.
And ultimately it will tend to 0.
But there is n here and n keeps increasing, right? So as you see, n is going to infinity here. So you are right with whatever you said, but the conclusion is not clear. Do you agree?
Yeah.
Right, like when I say p is, let's say, 3 over 4, then this expression will be like n times 1 over 4 raised to n minus 1. So can one of you tell me why does this, what will be the limit of this? There is some quantity which grows to infinity, there is another quantity which goes to 0, right? So what can you say about the product? Can one of you argue what would be the product? I mean the limit of the product? So this is nothing to do with topology. This is a very, very easy question. What is the answer? What is the limit of this sequence? What is the answer? This is a gate level question. I mean, I'm sure, I mean, maybe it's even simpler than a gate level thing. What is the answer? So maybe I'll just pick someone at random. Jayan, would you like to try and answer this question? Jayan, are you there? Lakhan, are you there? Okay. Yeah, Lakhan, would you like to give an answer to this question? What is the limit of this sequence?
I don't know, sir.
I mean, what is the limit of this sequence? N over 4 raised to n. How about this question? Have you heard about exponentially growing functions?
Yes, sir.
Yes. So can you tell me something about, so what is the numerator? Like numerator is what kind of a function? It's a linear function in n. Do you agree?
Yes, yes, sir.
Whereas the denominator is an exponentially fast growing function. Do you agree?
Yes, sir.
So which function will, grow faster, the linear function or the exponentially increasing function?
Exponentially increasing function.
So the numerator is growing relatively slower as compared to this thing. Do you agree?
Yes, sir.
So what do you think the answer should be? The denominator is growing very fast. The numerator is not growing that fast. So what will be the ratio converging to?
Sir, is going to 0, near to 0.
Right. So this is what one would expect, right? So of course there has to be a formal way to argue it out, but this is not the scope of this class. You should be able to do it on your own, that why such a thing will go to 0. But nevertheless, by the same argument, I hope you agree that if I choose a p which is a constant between 0 and 1, and this is a constant with respect to n, like whatever n you choose, your p will be fixed, right? So if you choose such a p, then this value, I hope you agree, will go to 0, which means that if you have a constant edge connection probability as n tends to infinity, the number of isolated vertices on an average will be 0. Is this okay? So that's what the conclusion is. If there is anyone who did not understand this last statement I made, please let me know, right? This is what I said, like whenever p is a constant, okay, the expected number of isolated vertices will go to 0, right? All right. So now my claim is that just because the number of isolated vertices does not go to 0, I mean goes to 0, that does not imply that the 0th Betti number also goes to 1. right? So I hope you agree that when the number of isolated vertices goes to 0, which means that you could end up with a scenario like this, right? So you could end up with a scenario. So let's say, you have a lot of vertices. So you can see that in this graph, you don't have isolated vertices. Nevertheless, you can see that Betty 0 is 3. So I hope you agree that the even though expected I 0 NP, okay, this goes to 0, this does not automatically imply that expected beta 0 NP, okay, this goes to 1. Do you agree with this statement? Does not automatically imply, okay, automatically imply. Do you agree with this statement? If you don't agree, please let me know. All right. Okay. So I'll presume most of you have understood what I said. So this is the scenario, right? So the summary of what we have done so far is that when P is a constant, expected value of these isolated vertices goes to 0. Okay, P is a constant implies this, right? However, this does not automatically imply something about this. This expected Betty number actually goes to 1. Right. So this is the summary of what we have discussed so far. So let's continue this study of isolated vertices. Right. So far we have looked at the case where P is a constant. Now let's ask what will happen if P is a function of n. Right. So P actually depends on n. Okay. So this depends on n, which means that as your n increases, we will sort of change the value of Pn. Right. So Pn, this depends on n, which is the number of vertices, right? And in particular, we will look at the case where Pn goes to 0, right? So why are we interested in the case where Pn goes to 0? Because if Pn goes to a constant, right? So let's say Pn goes to a constant, okay? So this is very similar to the case where Pn is a constant for all n, right? So this is similar to the case where Pn is maybe C, for all n. In this scenario also, we would expect that the number of isolated vertices actually goes to 0, right? So let's look at the case where Pn actually goes to 0, right? So Pn goes to 0. So since Pn goes to 0, okay, by a Taylor series approximation, one would be able to show that 1 minus Pn in this case, when Pn is very, very small, this can be approximated by e raised to minus Pn. I hope you all agree that by a Taylor series approximation, when Pn is very, very small, this can be approximated by e raised to minus Pn, right? Okay. So this will be, I hope you agree with this. So because of this, I can write this expectation. So recall the formula was n times 1 minus Pn raised to n minus 1. This I can write it as n times e raised to minus n minus 1 times Pn, right? So this is the expression. And now I'm going to ask what is the behavior of this as Pn goes to 0, right? So what I'll do is I'll take this particular form of Pn. Okay, why I choose this particular form will be clear soon, but for the time being, bear with me and let's all study this scenario where Pn has the form log n minus omega n over n. Okay, log n minus omega n over n, where omega n is such that omega n goes to infinity. Okay, so this goes to infinity. However, Pn itself goes to 0. So can one of you give me an example of an omega n which goes to infinity, however Pn goes to 0? Can one of you think of an example of such a omega n? So I'm asking you to think of a sequence which grows with n such that omega n goes to infinity but Pn goes to 0. Can one of you think of an example of omega n? Yes, Pankaj, please go ahead.
Is it log n?
So omega n is log n, is that what you said?
Yeah.
Okay, so let's try to see what happens. Omega is log n, then indeed Pn will be 0, right? And so of course Pn equals 0 means Pn goes to 0 and omega n goes to infinity, right? So this is a very, very simple example. Can you think of a more non-trivial example? How about omega n is maybe log n, right? So log n, right? So in this case, I hope you agree that log n, this will also grow to infinity, of course, very, very slowly, but Pn would be log n minus log n, right, by n. Is this okay? So in this sense, you can see that one can come up with several examples of omega n, right? So let us substitute this choice of Pn over here, right? So what we will end up with is that the expected value of isolated vertices here is n. So I have just copied this n over here, right? So whatever is this n, I have copied it over here. This thing I have split it as e raised to minus npn and e raised to pn, right? So e raised to minus npn times e raised to pn. And now what I'm doing is I'm going to substitute this part in this expression. So I hope you agree that n times pn, okay, n times pn is log n minus omega n. So e raised to minus npn is e raised to minus log n times e raised to omega n, right? So that is what I end up with over here, right? So now what I'm claiming is that this product is 1. Why is this product equal to 1? This is because e raised to minus log n is e raised to log of n raised to minus 1, and e raised to log of anything is that itself. So I'll end up with n raised to minus 1. So this n raised to minus 1 and n will cancel off with each other, and I'll be left with e raised to omega n times e raised to pn, right? Now since pn goes to 0, this expression will go to 1, and since omega n goes to infinity, this whole expression will go to infinity as n tends to infinity. So my claim is that when Pn is going to 0 roughly at the rate of log n over n, but there is some small perturbation because of omega n, right? So if this is the scenario, my claim is that here the number of isolated vertices actually grows to infinity, which means that in this particular scenario you will have infinitely many isolated vertices as n tends to infinity. So is there anyone who did not understand this calculation? Please let me know. Please let me know if you did not understand this calculation. All right, so I don't see any raised hands. So my claim is that whenever you have such a choice of Pn, that is log n minus omega n over n, right? So here, your Pn actually goes to 0, right? So here my claim is that expected value of beta 0 of nPn, this will also grow to infinity, right? Because you have so many isolated vertices, and each of these isolated vertices actually contribute one component, hence the total number of components, okay, should also grow to infinity. Now let's look at the opposite scenario, right? So the opposite scenario is, instead of looking at the case where Pn is log n minus omega n by n, right? So instead of looking at this scenario, let's look at the scenario where Pn is slightly above log n, right? So it is log n plus omega n over n, and again omega n is of the form that it is going to infinity, but Pn is going to 0, right? So like for example, your omega n could be like log n, right? So this is a function which grows very, very slowly to n. Nevertheless, it goes to infinity. So this means that Pn is just above log n over n. So let's now try to do the computation of expected value of INPN. So again, I have written down the same expression, right? However, because there is a plus omega n over here, right? There is a plus omega n over here. This entire expression will now be e raised to minus omega n times e raised to pn, and because this omega n goes to infinity, e raised to minus omega n will go to 0, right? And this will go to 1. So this product will actually go to 0. So which means that if you are slightly below log n over n, the number of isolated vertices is infinity. Whereas if you are slightly above the log n over n threshold, the number of isolated vertices actually just a minute, sorry. So if you are slightly above log n over n, the number of isolated vertices actually goes to 0. Now let's look at if you are at the log n over n threshold, which means that Pn is of the form log n plus some constant over n. So in the earlier scenario, you had minus omega n or plus omega n, and these expressions were growing to infinity. However, here you have log n plus c over n, right? This is the scenario, and again one can ask what is the expected value of INP over here, and you can do this computation one more time, and you will see that this expected value actually goes to e to the power minus c, which is a constant, because this c over here is a constant, and this c can be any real number, right? It can be a positive real number or a negative real number. And consequently, I hope you agree that by choosing a suitable value of c, this e raised to minus c can be made to be any number between 0 and infinity, right? So what is the summary? If Pn is log n plus omega n over n and omega n goes to minus infinity, then the expected number of isolated vertices grows to infinity. If omega n goes to a constant, right? So of course I dealt with the case where omega n equals c, but you can also look at the case where omega n converges to c. One can see that this expected number of isolated vertices goes to e to the power minus c, and the last cases where omega n grows to plus infinity, in this situation the expected number of isolated vertices is 0, right? So one can ask or one can based on this summary, one can conclude that log n over n is the threshold at which the expected number of isolated vertices undergoes a phase transition. By phase transition, I mean that just below log n over n, its value is plus infinity, and just above log n over n, its expected value is 0. And if you are very close to log n over n, then the expected value will be a number between 0 and plus infinity, right? So let me pause over here. If you have any questions with regards to what we just discussed, let me know. Let me know if you have any questions. Okay, I don't see any raised hands, which I find a bit surprising, but it's fine. Okay, so the conclusion is that we can conclude we can compute this expected value of isolated vertices and show that if Pn is of this form and omega n goes to minus infinity, then the expected number of isolated vertices goes to infinity. If it goes to a constant, the expected number of isolated vertices also goes to a constant. And when omega n goes to plus infinity, then the expected number of isolated vertices actually goes to 0. Is this okay? So in that sense, log n over n is the threshold at which this expected value undergoes a phase transition. Phase transition, by that I mean that it has a very different nature below this threshold, and it has a completely different nature above this threshold. So in this particular case, below the threshold, which is log n over n, the expected value is infinity. So you have infinitely many vertices. However, if you just slightly go above log n over n, the expected number of isolated vertices actually drops to 0. Right? So again, as I mentioned, if the expected number of isolated vertices goes to infinity, then indeed we can conclude that the 0th Betti number should also go to infinity. However, one cannot conclude that if the expected number of isolated vertices goes to 0, then expected Betti number also goes to 0, right? So this does not imply this. Do you agree? Because your graph may not have any isolated vertices. However, your graph could have a form something like this, where even though you have no isolated vertices, you can see that there are several components, right? So while I won't be able to prove this result because it's a bit hard, however, let me state the result. What is surprising is that this expected value of Betti 0, which is the number of components, in fact undergoes the same phase transition at log n over n, which means that below log n over n, the expected Betti numbers actually goes to infinity. Expected 0th Betti number actually goes to infinity, which is not surprising. However, if you just go above log n over n, then the expected value of the 0th Betti number actually goes to 0, which means that log n over n is the threshold after which the graph gets connected, right? So because once the graph gets connected, beta 0 is 1. Is this okay? So let me pause over here. If you have any questions with regards to this statement, please let me know. Right? This is one of the most fantastic results in random graph. It's very easy to state what the result is, but nevertheless proving that it is quite hard. So even though I have not proved it, right, I have given you some intuition in the language of this expected number of isolated vertices. So I've told you that before log n over n there are several isolated vertices, hence there are several components, and after log n over n there are no isolated vertices, which means and surprisingly, once you have no isolated vertices, the graph actually gets connected as well, right? So of course, this statement is as n tends to infinity. Nevertheless, this is true, right? So the answer is that below log n over n, this expected value goes to infinity, and above log n over n, this expected value goes to 1. Okay. So do you have any questions? Please ask questions if you have any. Yes, Jacob, please go ahead.
Why have we calculated for omega n being a constant? What was its purpose?
So your question was, what's the advantage of choosing this? Is that your question?
Yeah, why did you do that?
So we wanted. So you notice that so let me emphasize this. So Pn, if we choose it to be log n plus omega n over n, right? So we chose 3 different nature for omega n. One is that omega n goes to minus infinity, omega n goes to a constant, and omega n goes to infinity. So you see that these are the 3 different cases that can occur, that omega n goes to minus infinity, it goes to plus infinity, and it goes to a constant. Do you agree?
No.
If you choose a converging sequence for omega n, these are the 3 different kinds of limits that you can observe. Do you agree with that?
I don't have any background in that, so no problem.
So if you take a sequence, so you understand what is a sequence?
Yes, it's some
sequence means just a sequence of numbers. Is this okay?
Yes.
Right. So here I am choosing a sequence of numbers which is a function of n. That's what omega sub n means. Right. So like for example, I could choose log n. I could choose log n. Is this okay?
Okay.
Right. And I could also choose minus log n, minus log n, and so on. And I could also choose perhaps omega n is, let's say, 2 minus 1 over n, or 2 minus 1 over log n. Is this okay?
Okay.
Now, what will happen if n goes to infinity? What will happen to omega n? Can you tell me in this scenario? As n becomes larger and larger, what will happen to omega n?
That scenario, it will become 2.
It will go to 2. Do you agree? So you can see that whenever omega n converges to something, the limit, okay, can either be minus infinity, a constant, or some real number, or it will go to plus infinity. So we are dealing with all 3 cases. Is this okay?
Oh.
Does that answer your question? We have exhausting all possible cases.
Okay, the omega n example which you took corresponds to the constant case.
Omega n equals c, okay, is a special case of omega n converging to a constant. Do you agree?
Okay.
Right. So I wanted to sort of do that calculation quickly, but the same calculation will actually help you in this scenario as well. There is nothing complicated. Does that help?
Okay.
Right. So what is surprising is that the expected number of components in this Ador-Shreni graph actually has a behavior that is correlated with this number of isolated vertices. So whenever the isolated vertices is infinity, the expected number of components also grows to infinity. Whenever the isolated vertices goes to 0, okay, surprisingly, the number of connected components actually drops to 1, which means that the graph becomes connected. Right. So by studying how many isolated vertices are there, you can actually say something about the number of components in this graph. Is that okay? So that's the surprising conclusion, right? So the summary of this very simple exercise is that by choosing this, object which is combinatorially easy to study. right, which is this number of isolated vertices. So I sort of gave a demonstration that this is actually easy to study. One can actually identify its behavior and sort of check whether when the number of isolated vertices shows this behavior, does the number of components also show a similar behavior, and it was found that indeed that is the case. Yes, Pankaj, go ahead.
Does this result intuitively say if we have a very large n, then there is a high chance of having a connected component?
So that answer to your question depends on the value of P. Is this okay? Right. So as I said, if P is very small, right? Like let's say it is below this log n over n. So let's say omega. So maybe I'll say it is less than log n. Is this okay? Right. So if Pn is less than or it's like maybe some value like this, right? So you choose maybe n to be e raised to maybe some 100 or something, right? So in this case, Pn would be 100, or maybe I'll choose this as e raised to 100, right? So in this case, what Pn would be is e raised to 100 minus 100 by e raised to 100. So you can see that this actually will be a very small number. So if Pn is such a small number, right, what we are saying is that your graph will actually have lot of isolated vertices when in this scenario. However, if Pn is slightly above, right, so let's say Pn is of the form e raised to 100 plus 100 by e raised to 100, right? So what we are saying is that in this scenario, your graph will be connected with high probability. Does that answer your question, Pankaj?
The threshold was log n by n, right?
Log n by n, and here you notice I chose n to be e raised to 100, so it's a very big number.
Okay, but
right?
if the n is very large, then log n by n will be a very small number, isn't it?
So that's what I have, right? So log n is e raised to 100. Do you agree?
Okay.
Do you agree? When n is e raised to 100, log n is e raised to 100. Do you agree?
Yes.
And that's what I have written. And log n is my 100, and n is e raised to 100. So this is precisely log n minus log n over n. Is this okay?
Yeah.
Right. So of course, see, I'm making a hand wavy statement here because the claim is as n tends to infinity. However, you can sort of extrapolate and say that, when n is very large, one would expect that the graph to be almost connected when your connectivity threshold is above log n over n, and if it is below log n over n, then you would expect to see lot of isolated vertices. That's what one would expect. Is this okay? Does that answer your question, Pankaj?
Yeah, thank you.
Okay, are there any more questions? Please let me know. Okay, so of course, I did something very simple. It's related to this Edo-Shreni graph. I didn't talk about anything related to simplicial complex, but the philosophy that I explained, which is that you have a hard object to study, which are these Betti numbers and things like that. You don't directly study its properties, you approximate it by a combinatorial object that is easy to study. So when I say combinatorial object, I mean something that is easy to count. Okay, so you approximate it by something that is easy to count, use its properties, and somehow see if those properties hold true for these topological quantities as well. So that philosophy is something that is common across the whole literature on random topology. Is this okay? So how you identify this the right combinatorial object to study, that is where the whole smartness lies. Is this okay? And in different scenarios, like here we chose isolated vertices, right? But when you're studying a different quantity, you have to choose a different combinatorial object to study. So which object to choose and so on and so forth. Okay, so that's where the whole genius lies in the literature concerning random topology. All right. So does anyone have any questions? Otherwise, I can move on to the next part. Which I'll sort of give a brief idea, and we can end this class thereafter. Are there any more questions? All right. So I don't see any raised hands, so maybe we can advance. right? So far I hope you all agree that we did something related to random graphs, but when we began, we sort of started talking about this topic of random simplicial complexes. Okay, so I want to give a flavor of such a random simplicial complex. Okay, so we can sort of generalize this Edo-Shreni graph, okay, to a random simplicial complex and ask what is the behavior of the different Betti numbers. So one of the simplest way in which we can generalize or build a simplicial complex on top of an Edo-Shreni graph is what is called as a clique complex. Okay, so now let me explain what is a clique complex. So a clique complex is a simplicial complex, but it's a special kind of a simplicial complex. So what is special about the simplicial complex? Well, let's say you are given a graph G, right? So whenever I say you have given a graph G, I mean, I have given you a vertex set and the associated edge set. So you have a vertex set and an edge set, right? So what is the clique complex associated with this graph, right? So the first thing we have to understand is what is a clique. So a subset S of the vertices is said to be a clique in this graph if it is a complete subgraph. So let me explain it via an example. So let's say this is a graph, right? So this is not a complete graph because not all the possible edges are present. Like for example, 1, 5, 3, 5, all these edges are missing. So this is not a complete graph. On the other hand, these three vertices form a complete subgraph, meaning if you only look at the graph on these three vertices, all possible edges are present. Similarly, if you look at these four vertices, all possible edges are present. So you can see that all possible 6 edges are present. Similarly, if you look at this 2, 5, all possible vertices are present. However, if you look at 2, 3 and 5, okay, this edge is missing. That's why 2, 3, 5 doesn't form a clique. Whereas in this graph 1, 2, 3, 2, 5, 4, 5, 6, 7, okay, they form what are called as maximal cliques. So let me sort of emphasize that. So they form maximal cliques. So by that I mean that if you look at any of the subsets of these things, like if you let's say 1, 2, 3, so if you look at 1 and 2, so of course they form a clique, right? But what we are saying is that 1, 2, 3 forms a bigger clique, and similarly 4, 5, 6, 7 forms a bigger clique. Of course, if you look at these three vertices, they also form a clique, right? So in this sense, if you were asked what is the clique complex that is associated with this graph, you will sort of identify all the cliques that are present here. So the simplest cliques are these vertices themselves. So you list down all these 8 vertices. Then you list down all the edges, right? So you can see 1, 2, 1, 3, 2, 3, so on. All these edges you list down over here. Then you list down all these triangles, right? 1, 2, 3, 4, 5, 6, and so on. So all these 5 triangles you list down over here. So these are your two-dimensional faces in the clique complex associated with this graph. And then you also have this 4, 5, 6, 7, right? Because it forms a clique over here. But notice that I did not include, okay, 1, 2, 3, and 5, right? This does not belong to this clique complex. Okay, so this does not belong to this clique complex. So let me know if you have any questions on how we define this clique complex. Please let me know. I'd be happy to explain. Do you have any questions? Please let me know if you have any questions. Okay, surprising that nobody has any questions. Okay, it's okay. All right. So so one can, as I said, you can look at this Edo-Shreni graph, look at its clique complex. So this will be a random simplicial complex, which I will denote it as chi and p. And one can ask, what can you say about the different Betti numbers of this random simplicial complex, right? So these are the kind of questions that have been tackled in the last decade. In fact, one paper on this topic actually got published in this journal called as this Annals of Mathematics. So in some sense, this is the the journal that looks at the fundamental contributions in mathematics. So answering this question, like what can you say about the different Betti numbers of this simple random simplicial complex, that itself was very, very hard, and one had to do lot of what should I say, invent new theory and so on and so forth. And the effort that went into answering the the behavior of the Betti numbers of this simplicial complex was so profound that the paper actually got published in this top journal called as the Annals of Mathematics. All right. Okay, so I'll give you like a brief overview of how they went about computing the Betti numbers of this simplicial complex. Okay, so again, the idea is that you have to come up with a nice combinatorial object that approximates the Betti number of this. So in particular, let's say we are interested in knowing the kth Betti number of this simplicial complex, right? So what they do is they say that the kth Betti number can be upper bounded by the number of k dimensional faces in this simplicial complex, and one can also show, okay, I haven't shown it, and but one can show that one can also lower bound it by something like this. Okay, so this is the number of k dimensional faces. This is again the k dimensional faces. This is the k minus 1 dimensional faces, and this is the k plus 1 dimensional faces. So one can show that the kth Betti number is lower bounded by these two objects. Now these objects are again easy to study objects. So you study the properties of this, and one can then use the properties of this to say something about the properties of the kth Betti number. Okay, and that's what is the calculation that is done over here. Unfortunately, we are at the end of time, but those who are interested can go over it, and if these such topics interest you, you can write to me and we can talk a bit more about this. All right, so with this, I'll be ending today's class, and as I mentioned, my part of the course actually ends, and from the next class, Professor Vijay Natarajan will be teaching. So let me stop recording, and I would like to thank you all for being part of this discussion. Thank you.